What if we could build AI models that are not only smarter, but also more efficient and adaptable? That's the question we're tackling today on AI by AI. We're diving deep into the latest research that's pushing the boundaries of what's possible.
Exactly. We've got a packed agenda. First up, we're demystifying mixture of experts, or MoEs. Think of them as AI super teams, where different specialists handle different tasks. We'll break down how they work and why they're so powerful.
Then, we're unlocking the secrets to hyperparameter optimization for large language models. We'll explore the step law, a new approach that helps us fine-tune these massive models for peak performance. Hyperparameters are like the dials and knobs that control how an AI learns, and this research gives us a cheat sheet for setting them just right.
Next, we're exploring CogGRAG, a clever system that helps AI answer questions using knowledge graphs. Knowledge graphs are like interconnected maps of information, and CogGRAG helps AI navigate them more effectively. It's all about making AI better at reasoning and problem solving.
After that, we're showcasing Ling-Lite and Ling-Plus, two impressive mixture of experts models developed by AI at Ant Group. These models prove that you don't need unlimited resources to build cutting-edge AI. They've found innovative ways to train large models efficiently.
Finally, we're wrapping up with a look at object-centric world models for language-guided manipulation. This is all about teaching robots to understand and interact with the world around them using language. It's a big step towards more intuitive and capable robots.
So buckle up, because we're about to embark on a fascinating journey through the latest advancements in AI. Let's dive in. Okay, let's dive into this survey on mixture of experts, or MoE. It seems like these models are gaining traction as a way to handle the increasing complexity and size of AI tasks. The core idea is to dynamically select and activate only the most relevant submodels, or experts, for each input. This is different from traditional models where all parameters are activated for every input.
Exactly. So instead of one massive monolithic model, you have a collection of smaller specialized models. This divide and conquer strategy is particularly useful when dealing with diverse datasets, like those containing text, images, and audio. It helps to improve both performance and efficiency.
Right. The survey highlights two major challenges that MoEs address. First, the enormous computational resources required to train and deploy large models. Second, the difficulty in fitting heterogeneous data, which can limit a model's usability. MoEs tackle these by selectively activating experts, reducing computational costs and allowing for specialization.
And it's not just about efficiency. The survey mentions that MoEs can significantly improve model performance, especially when handling large-scale, multimodal data. Think about it. Each expert can focus on a specific type of data or task, becoming highly proficient in its area.
The paper outlines the basic design of MoEs, including gating functions, expert networks, routing mechanisms, training strategies, and system design. Let's start with the gating function. This is essentially the router that decides which experts get which data. The goal is to accurately discern the characteristics of both the input data and the experts, assigning similar data to the same expert or group of experts.
So the gating function needs to be smart about how it distributes the data. It also needs to ensure that the input data is distributed as evenly as possible among the experts. An uneven distribution can lead to model collapse, where some experts are underutilized and the model's performance suffers.
The survey mentions two main types of gating functions, linear and nonlinear. Linear gating, often using a softmax function, is popular due to its simplicity and effectiveness. The formula they give is a bit dense, but the key is that it calculates a gating value for each expert based on the input and then uses softmax to turn those values into probabilities. The top K function then selects the K highest scoring experts.
Top K. That's where you only activate the top K experts, right? This helps to reduce computational overhead. The order of top K and softmax can be switched depending on the specific requirements. Doing top K before softmax is faster, but might require an additional normalization step. Doing it after softmax gives you statistically meaningful activation weights, but is computationally more expensive.
Exactly. And when incorporating MoEs into existing models like transformers, it's common to replace the feed-forward network or FFN layer with an MoE layer. This is because the FFN layer typically constitutes a significant portion of the total computational cost in a transformer, and it exhibits higher sparsity, making it suitable for sparse activation mechanisms.
Okay, that makes sense. What about nonlinear gating functions? The survey mentions a cosine distance-based gating function used in GMOE for domain generalization tasks. How does that work?
Instead of a linear function, GMOE projects the input into a hypersphere space and compares it with the expert embeddings using cosine similarity. This helps the model handle cross-domain data and capture visual attributes, enhancing its generalization capability. There's also mention of gating functions based on the exponential family of distributions, which can analytically update the gating function during iterations.
Interesting. So the gating function is really about intelligently routing data to the right experts. Now let's talk about the expert networks themselves. What are some common designs?
In principle, each expert network can be an independent model. However, for efficiency, they're often integrated into a single network model, with specific layers replaced by MoE layers. The most common approach is to replace the FFN layer in a transformer with an MoE layer, as we discussed. But you can also apply MoE to the attention module, leading to a mixture of attention, or MoE.
MoA? That sounds cool. So instead of all attention heads processing every input, the gating function selects the top K attention heads based on the input's importance scores. This allows the model to focus on the most relevant attention heads, enhancing performance without significantly increasing computational costs.
Precisely. And there are variations on this, like switch head, which introduces MoE for each head's key, query, value, and output projection, and OH, which shares heads and uses a two-stage routing strategy. The survey also mentions applying MoE to CNN layers, creating convolutional mixture of experts, or CMoE, which leverages CNN's strengths in local feature extraction.
Okay, so we've got different gating functions and different expert network architectures. What about the routing strategy itself? How do you decide at what level to make those routing decisions?
That's where the routing level comes in. The survey outlines several common routing strategies: token level, modality level, task level, and other level routing. Token level routing makes decisions based on token representations, which is the most classic approach. Modality level routing routes tokens based on their modality, like text or image. Task level routing determines routing based on task IDs, which is useful for multitask learning.
So token level is like saying this word goes to expert A, modality level is like all the image data goes to expert B, and task level is like this translation task goes to expert C. Got it. What about training these MoE models? I imagine it's not as straightforward as training a dense model. Auxiliary loss functions like load balancing losses are used to ensure that all experts are utilized effectively, right? To prevent model collapse, where a few experts handle most of the inputs.
Exactly. The survey mentions importance and load loss functions, which aim to balance the influence of expert importance and load distribution. The switch transformer simplifies this approach, trading a slight reduction in accuracy for improved efficiency. Expert capacity, which refers to the maximum number of data points each expert can process, is also a key consideration.
And expert selection strategies like Top K help to increase model capacity without proportionally escalating computational costs. Introducing randomness into the expert selection process can also encourage exploration and prevent over-reliance on specific experts.
Right. And dynamic expert selection mechanisms like top P routing can adaptively adjust the number of activated experts based on input complexity. Pipeline design is also crucial for maximizing resource utilization and ensuring stable convergence. BPR, or batch priority routing, prioritizes important samples for processing, achieving sparsity reuse.
Okay, so we've covered the basic design, gating functions, expert networks, routing strategies, and training techniques. What about the system design aspects? How do you optimize MoEs for computation, communication, and memory?
The survey highlights that MoE's non-uniform workload distribution and dynamic expert selection impose strict requirements on the system. For computation, the goal is to mitigate the issue of non-uniform workload distribution, where some experts are idle while others are overloaded. Techniques like unified distribution layouts and gradient-based routing selection methods can help.
And for communication, the challenge is the all-to-all communication pattern required to distribute input data to the experts. On-demand loading strategies, where weights are loaded into on-chip memory only when the corresponding expert is selected, can reduce pressure on memory bandwidth. Parallelization strategies, like data parallelism and model parallelism, are also important.
Precisely. And for memory, the issue is the large number of parameters in MoE models. Parameter migration strategies, which leverage the memory space of multiple devices, and hierarchical storage management schemes, which integrate local high-speed caches with remote slower storage, can help to address this.
Okay, that's a good overview of the basic designs. Now the survey also delves into how MoEs are being used in various machine learning paradigms. Let's start with continual learning. How are MoEs helping to address the catastrophic forgetting problem?
In continual learning, the goal is to build an agent that can continuously learn new tasks without forgetting previously acquired knowledge. MoEs can help by dynamically selecting the most appropriate submodel for each input, allowing the model to handle diverse tasks without a substantial increase in computational overhead. The idea is that experts specialize in different tasks, mitigating forgetting.
So each expert becomes an expert in a specific task, and the gating function routes the data to the appropriate expert. The survey mentions CNDPM, HVCL, and lifelong MoE as examples of MoE-based approaches for continual learning. What are the key ideas behind these?
CNDPM uses a Bayesian nonparametric framework to dynamically expand the number of expert models. HVCL leverages multiple experts to alleviate problems in hierarchical variational continual learning. Lifelong MoE introduces new experts for new data distributions and uses regularization-based strategies to retain knowledge for old tasks.
And with the rise of pre-trained models, there's been a focus on prompt-based continual learning. How are MoEs being used in that context?
The survey mentions MoE, or mixture of task-specific experts, where a task-specific adapter or expert is trained for each new task. An expert evaluation strategy and an expert peer voting mechanism are used to enhance feature robustness and reduce cross-task feature overlap. There's also PMoE, which uses shallow layers for general knowledge and deep layers for new knowledge, progressively adding new experts to deep layers.
Okay, that makes sense. So MoEs are being used to create specialized experts for different tasks in continual learning, helping to mitigate forgetting and improve performance. What about meta-learning? How are MoEs being used to learn to learn?
The core of meta-learning is enabling models to quickly learn new tasks from a small amount of data. MoEs can enhance this rapid learning capability by leveraging multiple expert models to learn the distinct core features of each domain. By capturing the differences and connections between various tasks, MoEs can promote more efficient learning and adaptation of new tasks.
The survey mentions MoE-NPs, or mixture of expert neural processes, as an example. How does that work?
MoE-NPs uses multiple latent variables and discrete assignment latent variables to construct a mixture of NPs experts. The multiple latent variables define various functional priors, and the discrete assignment variable controls the expert selection for each data point in prediction.
And MoEs are also being used in domain adaptation, where the goal is to adapt a model trained on one domain to perform well on a different but related domain. How does that work?
In domain adaptation, MoEs can explicitly characterize the relationships between different source domains and the target domain. The prediction for a target example will be based on a weighted combination of all experts' predictions, where the weights capture the similarity of the target example with each source domain.
Okay, so MoEs are helping to capture the nuances between different tasks and domains in meta-learning, allowing for faster and more efficient adaptation. What about multitask learning? How are MoEs being used to learn multiple related tasks simultaneously?
Multitask learning aims to improve the generalization ability and performance of a model by learning multiple related tasks simultaneously. MoEs can intelligently select the most suitable submodel for processing based on the characteristics of the input data, naturally decoupling different tasks and effectively handling the complex relationships between them.
The survey mentions MMOE, or multi-gate mixture of experts, as an important variant. How does that differ from a standard MoE?
MMOE sets up a separate gating network for each task. This allows the gating network to select different expert networks based on the specific characteristics of the current task, decoupling each task into different gate functions. This avoids the mutual interference of tasks with large differences.
And MOEs are also being used in multitask reinforcement learning, where the goal is to promote the learning of diverse skills by agents. How does that work?
In multitask reinforcement learning, MOEs can help to ensure the diversity of learned representations. For example, MORE, or Mixture of Orthogonal Experts, utilizes multiple expert models responsible for generating different representations, encouraging the model to learn more diverse skills. The Gram-Schmidt orthogonalization method is used to force each expert to generate mutually orthogonal features.
Okay, so MOEs are helping to decouple tasks and learn diverse skills in multitask learning. What about reinforcement learning in general? How are MOEs being used to learn policies by interacting with the environment?
In reinforcement learning, MOEs can enhance agents' flexibility in responding to diverse demand patterns and environmental changes, improving overall performance. One notable direction is modular RL, which breaks down complex RL problems into smaller modules and builds multiple subagents to handle specific aspects of the task.
So each expert becomes a specialist in a specific aspect of the RL problem. The survey mentions MMRL, MACE, and TRL as examples of MOE-based approaches for reinforcement learning. What are the key ideas behind these?
MMRL uses multiple modules, each with a dynamics model and a controller, where the state predictions and action outputs are a weighted combination of all module outputs. MACE uses multiple actor-critic pairs for learning terrain-adaptive dynamic locomotion skills. TRL transfers skill knowledge in multitask RL, with both actor and critic consisting of a hierarchical structure with experts and a gating network.
And more recently, there's been a surge of interest in using MOEs in RL due to their success in LLMs. How are MOEs being incorporated into the DNNs used in value-based deep RL approaches?
The survey mentions that the performance of various deep RL algorithms can be significantly improved by incorporating soft MOEs to replay the penultimate layers. This has been observed in different RL setups, such as online RL, offline RL, and RL with a small amount of interactions.
Okay, so MOEs are helping to improve performance and adaptability in reinforcement learning, both in modular RL and in deep RL approaches. Now let's shift gears and talk about the theory behind MOEs. The survey mentions that the theory is largely underexplored. What are some of the key areas that have been investigated?
Most of the theory development so far has focused on simple models. Early studies sought to understand the approximation capacity of MoE models, investigating the convergence rate for hierarchical MoE models with different types of experts. More recent studies have aimed to characterize the convergence of MLE, or maximum likelihood estimator, for MoE models with different gating functions for regression problems.
So the focus has been on understanding how well MOEs can approximate functions and how quickly the parameters converge. What about the theoretical understanding of MOEs for classification problems?
That's less explored. The survey mentions one study that investigates the classification problem with MoE models, including softmax gating and multinomial logistic expert models, establishing convergence rates for density estimation and parameter estimation. It also discusses the inefficiency issues encountered by the gating function when some expert parameters vanish.
And what about the theoretical understanding of MOEs in deep learning, with more complex expert models like CNNs?
That's even more elusive due to the limited understanding of deep neural networks in general. The survey mentions a few studies that have made initial attempts to understand the behaviors of MOEs in deep learning, showing that MOEs can automatically learn the cluster structure of data and dynamically route data to the most suitable expert.
Okay, so the theory is still catching up to the empirical successes of MOEs, especially in deep learning. Now let's move on to the applications. The survey focuses on computer vision and natural language processing. Let's start with computer vision. How are MoEs being used in image classification?
In image classification, MoEs are being used to improve performance, efficiency, and stability. vMoE replaces the MLP layers in vision transformers with sparse MoE layers, scaling the model to billions of parameters. VIMO introduces the concept of shared experts, where a shared expert handles common knowledge, while other specialized experts focus on specific knowledge.
And what about object detection? How are MoEs being used to detect and locate objects in images?
In object detection, MoEs are being used to improve the model's ability to understand and process multi-source datasets. DAMX proposes a data-aware MoE architecture, training different experts to learn data from different sources, enhancing the model's generalization capability.
Okay, so MoEs are helping to handle diverse datasets and improve generalization in object detection. What about semantic segmentation, where the goal is to classify each pixel in an image?
In semantic segmentation, MoEs are being used to achieve a good balance between computational complexity and representational capacity. Deep MoE combines convolutional networks with shallow embedding networks and multi-head sparse gating networks, dynamically selecting and executing partial networks at each convolutional layer.
And finally, what about image generation? How are MoEs being used to produce realistic and diverse images?
In image generation, MoEs are being used to enhance the quality of generated images, improve the diversity of outputs, and enrich detail representations. Raphael introduces two types of MoE models for temporal control and spatial settings during generation, allowing each text token to learn specific visual features through specialized experts.
Okay, so MoEs are being used across a wide range of computer vision tasks, from classification to generation. Now let's move on to natural language processing. How are MoEs being used in natural language understanding?
In natural language understanding, MoEs are being used to enable machines to understand and interpret human language, performing tasks such as intent recognition, entity extraction, and semantic analysis. GLAM introduces an MoE architecture to make the training and inference processes more efficient. MoE SLU aims to mitigate the impact of ASR errors on spoken language understanding performance.
And what about natural language generation? How are MoEs being used to transform structured data or concepts into natural and fluent text?
In natural language generation, MoEs are being used to achieve diverse and precise language expression, handling interference in multitask learning, and enhancing model specialization. In text generation, MoEs are being used to leverage multiple experts to collaboratively generate high-quality sentences. In machine translation, MoEs are being used to improve translation accuracy and fluency, handling complex scenarios involving multiple languages and domains.
And finally, what about multimodal fusion, where the goal is to integrate information from text and other modalities?
In multimodal fusion, MoEs are being used to dynamically adjust the importance weights of different modalities based on their characteristics, enabling effective integration and utilization of information from different sources. iMoE is the first large-scale multimodal mixture of experts model simultaneously processing image and text data and aligning their representations through contrastive learning.
Okay, so MoEs are being used across a wide range of natural language processing tasks, from understanding to generation to multimodal fusion. Now let's wrap up by discussing the future directions for MoE research. What are some of the key challenges and opportunities?
The survey outlines several key future research directions. First, training stability and load balancing, ensuring balanced utilization of experts. Second, training and system efficiency, optimizing hardware-software co-design and reducing communication overhead. Third, architecture design, determining the optimal number of experts and their specialization. Fourth, theory development, improving the interpretability of MoE models and understanding their behavior. Fifth, tailored algorithm design, integrating MoEs with other learning frameworks. And sixth, new applications, exploring the potential of MoEs in other domains beyond NLP and computer vision.
So, there's still a lot of work to be done to fully unlock the potential of MoEs. but it's clear that they're a promising approach for handling the increasing complexity and scale of AI tasks. Thanks for walking me through this survey.
My pleasure. It's exciting to see how MoEs are evolving and being applied to so many different areas. Okay, let's dive into this paper on hyperparameter scaling laws for large language model pre-training. The core idea is that finding the right learning rate and batch size is crucial for LLM performance, but it's computationally expensive, especially at scale. They've discovered some universal scaling laws that can help.
So instead of just randomly trying different combinations, they've found patterns. What exactly are these scaling laws?
Exactly. They found that the optimal learning rate follows a power law relationship with both the model size, number of parameters, and the dataset size, number of tokens. The optimal batch size, on the other hand, scales primarily with the dataset size. Think of it like this. As your model and data grow, you can predict how your learning rate and batch size should change to maintain optimal training.
Power law. That sounds a bit technical. Can you break that down?
Sure. A power law relationship means that if you increase the model or data size by a certain factor, the optimal learning rate changes by a related factor, raised to some power. It's not a simple linear relationship. For example, if you double the data size, the learning rate might change by a factor of 2 to the power of 0.3 or something like that. The key is that it's a predictable mathematical relationship.
Got it. So they're saying there's a formula to figure out the best learning rate and batch size based on the size of the model and the data.
Precisely. And they call it the step law. They claim it's a plug-and-play formula that can significantly reduce the need for extensive hyperparameter tuning. They even say their estimated values are only 0.09% away from the globally optimal performance found through exhaustive search.
That's a pretty bold claim. How did they arrive at this step law?
Through a massive empirical study. They trained 3,700 LLMs from scratch, varying model sizes and hyperparameters, and processed about 100 trillion tokens. That's nearly 1 million NVIDIA H800 GPU hours. They then analyzed the results to identify these scaling laws.
Wow, that's a serious commitment of resources. So what makes their approach different from previous attempts to find these scaling laws?
Good question. They highlight that previous research often focused on either theory-driven or data-driven approaches, but they didn't fully capture the interplay between data recipe, the composition of the training data, model shape, model sparsity, and data sizes. Their work aims to provide a more comprehensive understanding by considering all these factors.
Model sparsity. What does that mean in this context?
Model sparsity refers to how many of the model's parameters are actually used during computation. A dense model uses all its parameters, while a sparse model, like a mixture of experts MoE model, only activates a subset of its parameters for each input. MoE models are interesting because they can scale to very large sizes without requiring as much computation as a dense model of the same size.
Okay, so they're saying their step law works for both regular dense models and these more efficient sparse MoE models.
Exactly. They found that the scaling laws hold across variations in model sparsity, training data distribution, and model shape. This is a key contribution because it suggests that the underlying principles governing hyperparameter optimization are more general than previously thought.
The paper also mentions something about a convex optimization landscape. What's that all about?
That's a crucial point. They discovered that the loss landscape, think of it as a map of how the training loss changes as you adjust the learning rate and batch size, is convex under fixed model and data size conditions. Convexity means that there's essentially a single valley or optimal region. This implies that there's an optimal hyperparameter plateau, making it easier to find good hyperparameter settings.
So it's not a bumpy, chaotic landscape with lots of local minima where the training could get stuck?
Precisely. The convexity suggests a smoother, more predictable landscape, making optimization more reliable. They even provide visualizations of this loss landscape, showing how the training and validation loss change with different learning rate and batch size combinations.
Interesting. What about the data itself? Did they use a specific data set, or did they experiment with different types of data?
They trained their models on a dataset that includes web text, mathematical content, and code. They also experimented with different data distributions, including bilingual corpora and code-heavy datasets, to test the robustness of their scaling laws.
And their step law held up even when the data distribution changed.
Yes, remarkably so. They found that their formula maintained predictive accuracy across these different distributions, suggesting that it's not overly sensitive to the specific composition of the training data.
That's pretty impressive. So what are the practical implications of this research?
The main implication is that it can significantly reduce the computational cost of pre-training large language models. Instead of spending vast amounts of resources on hyperparameter tuning, researchers and practitioners can use the step law to estimate optimal learning rates and batch sizes, saving time and money. It also makes it easier to scale LLMs to even larger sizes, as we have a better understanding of how to adjust hyperparameters as the model and data grow.
Are there any limitations to their findings?
Yes, they acknowledge that their findings are primarily data-driven. While they've empirically validated their scaling laws, they call for future work to develop a more theoretical understanding of why these power law relationships exist. This could potentially enhance their predictive power and generalizability beyond the empirically validated domain. Okay, let's dive into this paper. Human Cognition-Inspired RAG with Knowledge Graph for Complex Problem Solving. Sounds like a mouthful, but it's all about making large language models, or LLMs, better at answering tricky questions.
Right? LLMs are powerful, but they can struggle with complex reasoning and sometimes just make stuff up, which they call hallucinations. So how does this paper propose to fix that?
They're tackling it with something called CogGRAG, which stands for Cognition-Inspired Graph-Based Retrieval Augmented Generation. Basically, it's a system that tries to mimic how humans solve problems by breaking them down into smaller parts and checking their work.
So it's not just throwing more data at the LLM, it's about structuring the process. How does it actually work?
Exactly. CogGRAG has 3 main stages. First, there's decomposition, where it breaks down a complex question into simpler sub-questions, creating a mind map of sorts. Then comes retrieval, where it pulls relevant information from a knowledge graph, both for the individual sub-questions and the connections between them. Finally, there's reasoning with self-verification, where it answers the sub-questions and then checks its own work to make sure the answers make sense.
Okay, let's unpack that. What's a knowledge graph in this context?
Think of it as a database where information is stored as interconnected facts. Each fact is a triple: entity, relation, entity. For example, Barack Obama is president of United States. These triples are linked together to form a graph showing how different pieces of information relate to each other.
Got it. So the retrieval stage is about finding the right triples in the knowledge graph to answer the sub-questions?
Precisely. And it does it on 2 levels, local and global. Local retrieval finds information directly relevant to each sub-question. Global retrieval identifies connections between the sub-questions, ensuring a more comprehensive understanding.
And what about this self-verification stage? That sounds interesting.
That's where it gets really clever. It uses 2 LLMs, one to do the reasoning and another to verify the results. It's like having a second pair of eyes to catch any errors or inconsistencies. If the verification model finds a problem, it prompts the reasoning model to rethink its answer.
So it's actively trying to avoid those hallucinations we talked about earlier.
Yep. And to further reduce hallucinations, the system is also prompted to respond with "I don't know" if it can't find a reliable answer, rather than making something up.
That makes sense. So how well does CogGRAG actually perform?
The paper presents experiments on several benchmark datasets for knowledge graph question answering, or KGQA. They compared CogGRAG against other methods, including LLMs without external knowledge, LLMs augmented with knowledge graphs, and other graph-based RAG systems.
And the results?
CogGRAG outperformed the baselines in most cases. It seems that breaking down complex problems and verifying the reasoning process really does improve accuracy.
That's promising. Did they test it with different LLMs?
Yes, they used ALMA 213b, 8b, and Quen 2.57b. CogGRAG consistently performed well across all of them, and the performance generally improved with larger models.
Okay, so it's not just a one-trick pony. What about the limitations? Anything they haven't solved yet?
They acknowledge that the decomposition and self-verification steps add computational overhead, so there's room for improvement in terms of efficiency. Also, CogGRAG is currently designed for knowledge graphs and can't directly handle document-based knowledge sources. They plan to address this in future work.
So, it's a step in the right direction, but still needs some tweaking. Overall, it sounds like a pretty solid approach to improving the reliability of LLMs for complex problem solving.
Definitely. By mimicking human cognitive processes, CogGRAG offers a promising way to reduce hallucinations and enhance the reasoning capabilities of LLMs. All right, let's dive into this paper. Every flop counts, scaling a 300B mixture of experts LLM without premium GPUs. Sounds like they're tackling the big issue of making these massive models more accessible.
Exactly. The abstract mentions training large mixture of experts, or MoE models. For those who aren't familiar, MoE models are like having a team of specialists within one big AI. Instead of one giant neural network, you have multiple smaller expert networks, and a router decides which expert is best suited to handle a particular piece of input.
Right, so it's a divide-and-conquer approach. This paper introduces two models, Ling-Lite and Ling-Plus. Ling-Lite has 16.8 billion parameters, but only 2.75 billion are activated at any given time. Ling-Plus is much bigger with 290 billion parameters and 28.8 billion activated. That's a huge difference in scale.
It is. And the key takeaway is that they achieved performance comparable to industry benchmarks, but with significant cost savings. They claim a 20% reduction in computing costs by using lower-spec hardware during pre-training. That's a game-changer for smaller research teams or companies with limited resources.
Definitely. They highlight three main areas of innovation: optimizing model architecture and training, refining anomaly handling, and enhancing model evaluation efficiency. Plus, they used knowledge graphs to generate high-quality data, which improved the model's tool use capabilities.
Tool use is super important. It means the model can interact with external APIs and services, making it much more useful in real-world applications. Think of it as giving the AI hands and feet to interact with the digital world.
The introduction really sets the stage. They talk about the rise of LLMs and how MoE models are outperforming dense models in some areas. But the high cost of training MoEs, especially with those fancy H1, H100, and H800 GPUs, is a major barrier.
Yeah, those high-performance accelerators are in short supply and high demand. It's like trying to get tickets to a Taylor Swift concert. So they're addressing a real bottleneck in AI development.
They also point out the imbalance in resource demand. High-performance resources are needed during peak usage, leaving many researchers with persistent shortages. This is where their approach of using more widely available, lower-performance accelerators comes in.
It's about finding a balance between cost and performance. They mention the challenges of cross-cluster and cross-device compatibility, resource synchronization, and optimizing cost-performance trade-offs. Training these models isn't just about throwing more hardware at the problem. It's about smart engineering.
Exactly. They use their open-source project, DLR Rover, to manage workloads across different hardware. They also developed XSpotimer, a lightweight debugging tool, and DIT, an asynchronous training strategy to improve efficiency. Storage optimization is also key, reducing I/O overhead by 50%.
Or elastic distributed training sounds particularly interesting. It's an asynchronous training approach that reduces training time by up to 66.1%. That's a huge speed up. Asynchronous training basically means that different parts of the model can be updated at different times, rather than waiting for everything to synchronize after each step.
They also have a multi-level anomaly detection system and automated checkpoint recovery to handle hardware errors and loss anomalies. Training these massive models is a delicate process, and things can go wrong quickly.
And to improve tool use, they're leveraging knowledge graphs to generate high-quality data and using self-reflective multi-agent dialogues for adaptive tool learning. It's like teaching the AI to learn from its mistakes and improve its problem-solving skills.
The paper goes into detail about their infrastructure, focusing on scaling and efficiency. They use DLR to optimize workloads and XPU-Timer for performance monitoring. They also developed Pcache, an all-flash distributed file caching system to handle the massive datasets involved.
Pcache is designed to address the challenges of multi-cluster environments and device multi-tenancy. It optimizes I/O performance using techniques like fuse, metadata caching, and a worker selection strategy. They even co-designed it with Megatron, a popular training framework, to reduce checkpoint writing latency by 50%.
They also developed Babel, a data synchronization middleware to efficiently transfer massive data sets across clusters. It uses parallel metadata prefetching and data verification techniques to ensure data consistency. It sounds like they've really thought about every aspect of the training pipeline.
Absolutely. And for inference, they propose Flood, an efficient offline inference framework that uses a fully pipeline parallel architecture. This reduces communication overhead and simplifies model adaptation. They also introduce a segment cache mechanism to maximize accelerator resource usage.
Moving on to pre-training, they used a diverse corpus of 9 trillion tokens, including Chinese, English, and code. They developed specialized data cleaning pipelines and a quality assessment framework to ensure high-quality data. They also fine-tuned models to identify high-quality data samples and conducted sampling experiments to optimize data selection.
Data curation is so crucial. It's not just about the quantity of data, but the quality. They even curated a large-scale dataset focused on programming and mathematical reasoning, using advanced filtering models to ensure relevance.
Their model architecture is also interesting. They use a fine-grained expert strategy, scaling the number of experts while reducing the size of each expert. This promotes specialization and allows the model to encapsulate a wider range of knowledge. They also introduce a shared expert to provide general abilities.
And to improve training stability, they use a stochastic routing warm-up mechanism and norm head, a normed LM head for token prediction. These techniques help prevent expert overload and stabilize the output norm of the LM head.
They also delve into scaling laws, analyzing the relationship between batch size, learning rate, and compute budget. They found that the scaling behaviors of batch size and learning rate for MoE models are consistent with those observed in dense models. And they found that MoE architectures are about 3 times more efficient than dense architectures in terms of compute required to achieve the same performance.
That's a significant efficiency gain. It really highlights the potential of MoE models for large-scale applications. They also describe their training recipe, including initial pre-training, long context pre-training, annealing, and a skip loss spikes and sample retry mechanism.
The post-training phase involves supervised fine-tuning, SFT, and direct preference optimization, DPO. They use synthetic data to scale their SFT dataset and implement quality assurance measures, such as rule-based filtering and LLM-based judging.
They also address data redundancy by implementing a semantic-based deduplication method. And for DPO, they use a data packing strategy to increase training speed and conduct a format-focused training phase to improve the clarity and structural organization of responses.
To enhance the model's performance on long context tasks, they synthesize long context instruction data and implement a progressive fine-tuning strategy. They also use reinforcement learning optimization to improve alignment with human preferences.
And to improve tool use, they focus on synthesizing high-quality tool use data and adaptive tool learning. They train the models to interact with public APIs, application APIs, and synthetic APIs generated by their knowledge graph technology.
In the results section, they compare Ling-Lite and Ling-Plus to other state-of-the-art open-source models. They optimize their evaluation benchmarks to address instability in the early stage and lack of instruction following. They also link evaluations to training to identify issues in the training process.
They found that Ling-Lite's performance is very close to that of Qwen 21587B, while Ling-Plus's performance is comparable to that of Qwen 2572B. They also achieve strong results on tool use benchmarks. And importantly, The Ling-Plus model achieves almost identical results on each benchmark regardless of which AI accelerator is used.
They also evaluate the model's safety performance using datasets like arena safety and C-values. They found that Ling-Plus demonstrates a better overall trade-off between safety and refusal.
Finally, they share some bitter lessons learned during training, including challenges related to training stability and cross-platform alignment. They discuss issues like loss spikes, loss divergence, and expert load imbalance, and they share strategies for mitigating these issues.
Overall, this paper presents a comprehensive approach to training large-scale MoE models with limited resources. They introduce several innovative techniques and achieve impressive results. It's a valuable contribution to the field and could help democratize access to advanced AI.
Definitely. By focusing on efficiency and accessibility, they're paving the way for more sustainable and inclusive AI development. And the fact that they're open sourcing their models and code is a huge win for the community.
All right, let's dive into this paper on object-centric world models for language-guided manipulation. It's all about getting robots to understand and act on instructions in a visual environment.
Sounds cool. So what's a world model in this context?
Think of it as a simulator inside the robot's brain. It allows the robot to predict what will happen next if it takes a certain action. This is crucial for planning and learning.
Okay, makes sense. And why object-centric?
Instead of looking at the whole scene as one big blob of pixels, the model focuses on individual objects. It identifies and tracks them. This is done using something called slot attention, which basically breaks down the scene into distinct slots, each representing an object.
So like one slot for a blue block, another for a red one, and so on.
Exactly. And the cool thing is, the model learns these object representations without needing someone to explicitly label them. It figures it out on its own.
Nice. How does language come into play?
The model takes language instructions, like put the blue block next to the pentagon, and uses them to predict how the objects in the scene should move. It's like telling the robot what you want it to do, and it figures out the steps to get there.
So it's predicting future states based on what you tell it to do.
Precisely. And the authors argue that this object-centric approach is more efficient than just generating videos of what might happen, which is what some other models do. Those video generation models, especially ones using diffusion models, can be super computationally expensive.
Diffusion models. Aren't those the things behind a lot of the AI image generators?
Yep, they're powerful but resource-intensive. This object-centric model aims to be a more lightweight alternative, especially for tasks where recognizing and manipulating objects is key.
Got it. So what did they actually do in the paper?
They built this object-centric world model called LS Slotformer and tested it on a simulated robotic manipulation task. They compared it to some state-of-the-art video generation models, and it outperformed them in terms of both success rate and computational efficiency.
What kind of tasks are we talking about?
Simple things like moving blocks around on a table, but guided by language instructions. The robot has to see the blocks, understand the instruction, and then act to complete the task. That's why they call it a visual-linguo-motor control task.
Okay, so it's not just about moving blocks randomly, it's about following instructions to do it.
Exactly. And they found that their model was better at generalizing to new situations, like using different colored blocks or performing slightly different tasks. They also explored different ways to predict actions based on these object-centric representations.
Interesting. So how does this slot attention thing actually work?
It's a mechanism that allows the model to focus on different parts of the image and assign them to these slots. Think of it like having a spotlight that shines on each object in the scene one at a time. The model then learns to represent each object independently in its corresponding slot.
And this helps with predicting future states.
Definitely. Because the model knows where each object is and how it's interacting with other objects, it can more accurately predict how the scene will change when the robot takes an action. It's like having a mental model of the world that's organized around objects.
So what are the limitations of this approach?
Well, the authors acknowledge that their experiments were all done in a simulated environment. They suggest that future work could focus on extending the model to more complex real-world scenarios. Also, the model assumes a fixed number of objects in the scene, which might not always be the case in the real world. They also point out that the model is deterministic, meaning it doesn't account for uncertainty or randomness in the environment.
Right, real-world robots have to deal with a lot more messiness than simulated ones.
Exactly. But overall, this paper presents a promising approach to building more efficient and effective world models for robotics. By focusing on objects and using language to guide predictions, they've taken a significant step towards creating robots that can truly understand and interact with their environment. Well, that was quite the journey through the AI landscape. We covered a lot of ground, from making models more efficient with mixture of experts to finding the sweet spot for training with those hyperparameter scaling laws. It's amazing how much progress is being made on both fronts, squeezing more performance out of existing resources and figuring out the best way to train these massive models in the first place.
Absolutely. And it's not just about raw power. Seeing how researchers are building in reasoning and verification, like with that knowledge graph approach, is really exciting. It's about making AI more reliable and trustworthy, not just bigger and faster. Plus, the work being done to make these models more accessible, training them without needing top-of-the-line hardware, is crucial for democratizing AI research.
Definitely. And let's not forget about getting robots to understand and interact with the world around them. That object-centric approach is a clever way to bridge the gap between language and action, bringing us closer to robots that can truly understand and follow our instructions.
It's all connected, isn't it? More efficient models, better reasoning, easier access, and more intuitive interaction. It feels like we're building the pieces of a puzzle that are starting to fit together. Who knows what breakthroughs the next few months will bring?
Exactly. It's a constantly evolving field, and we're excited to keep exploring it with you. Thanks for tuning in, and we'll catch you next time for another deep dive into the world of AI.